In the last video, we were taking a look at complex conjugates, and I ended you guys off with looking at one property over here, which was a complex number multiplied by its conjugate was going to be a part of the realm of real numbers. So why exactly is that going to be the case? Well, whenever we want to figure out why something is, the best bet you're going to have is to return back to just the most simple way of going about doing it. So how about we replace z with what z is, and we replace z bar with what z bar is. So what do I mean by that? Well, what exactly is z over here? We know that's a complex number. So z is equal to x, which is a real number, plus I multiplied by y. And then we learned that the conjugate is going to be z bar is equal to x minus I multiplied by y. So let's just go ahead and replace these numbers and go ahead and solve it like that. So z multiplied by its conjugate is going to be x plus iy, x minus iy, and we just go ahead and we multiply this out straight up. So x multiplied by x is going to be x squared. Then we'll have x multiplied by negative iy. In this case, that's going to be iyx. Then we have positive iy multiplied by x. This is going to give us a term that's going to cancel that first one out. And then we're going to have iy multiplied by negative iy, which is going to be negative I squared y squared. Well, first thing we notice, we can cross off these two terms because they are opposite. And then we see we're going to have, if we went ahead and got rid of those, we would have this over here. And you might be saying, well, this kind of looks like it's the setup of a complex number, right? How is this going to be a real number? The important thing, right? The important thing we need to remember with complex numbers is that I squared is equal to negative 1. Whenever we have I squared, we can go ahead and replace this with negative 1. That's the whole point of these complex numbers, which means we see I squared over here. We can go ahead and we can replace them. This will be the same thing as x squared is equal to minus negative 1 multiplied by y squared, which would give you x squared plus y squared. We know that if x is part of the realm of real numbers, then x squared will be a part of the realm of real numbers. And then obviously if y is part of the realm of real numbers, then y squared will also be a part, which would clearly mean that when you're adding two real numbers to each other, you're going to get a real number. So in this case, this here is going to be, go ahead and put that, this here will be a real number. So that's why we would go ahead and we will get that when we're multiplying a complex number by its conjugate, you are going to get a real number. If you guys have questions about this, leave it below, but I think it's pretty simple where we're just going to, return to the definitions of both of these values that we have here and just multiply them, right? It's the easiest way to go about doing that. Now, with what we know over here, right, what would happen if we were to take the square root of z multiplied by its conjugate? Well, the square root of z being multiplied by its conjugate is going to be the square root of x squared plus y squared, right? We see this right here. This is clearly going to just take this over here and put it down here because we know they're equal to each other. So this is going to be the Euclidean length on r squared. And we're actually going to define this as something. We are going to define this over here. So the Euclidean length of z here, we're going to put these two bars around it. And we're going to go ahead and say that is going to be equal to the square root of z being multiplied by its own conjugate, which would be the square root of x squared plus y squared. And this is going to be a real number. So this will be this. Go ahead and write out here. This will be real number from 0 to point xy. Whoops, not the z, get rid of the z. Where we know that xy is z. That might seem a little bit confusing, so let's return to that plane that we had made in the first video, I believe it was. So we had this one over here, and this was our real numbers, right? So this is representing our real numbers, and we'll have this over here. So we are going to have point x, we'll have point y, and if we're asking for x squared plus y squared, well, think back to the Pythagorean theorem, right? Actually, sorry, the square root of this. The square root of this is going to give you your hypotenuse, right? your hypotenuse, right? Essentially, let's go ahead and chart this out over here. And then your hypotenuse here. Because if we think about this, right, this y length here, this is going to be y. And this length over here is simply going to be x. So the square root of those numbers squared is going to be your hypotenuse via the Pythagorean theorem, right? So, via Pythagorean theorem. So therefore, z bar, which is going to give you, in the sense, this x squared plus y squared, it's going to be a real number that's going to be from your origin here, 0, 0, to this point z over here, and this point z is going to correspond to xy as we just saw. So that is going to be a real number because it's going to be a real number squared multiplied by a real number squared, all under a square root. Doing those squares and square root operations and addition is not going to change the fact that it is a real number. We do not have the I squared is equal to -1 property involved in any possible way, which means that we are going to be free to do this and get a real number. So if that makes sense to you guys, then I think you guys have a pretty good understanding of what we have been looking on. We'll look at some more things with complex numbers and a few more things with conjugates. I'm sorry, I know I want to end off those conjugates. We'll look a little bit more at them in the next video. If you have any questions about this, leave them below. I'll answer you in under 24 hours. And if these videos helped you out at all, please subscribe. It means a ton. Thanks. See you in the next video.